So today's lecture is on rotational spectroscopy, and we are not in this semester going to do a lab experiment that is pure rotation. So I want to make sure you don't get confused. We're studying this because it teaches us about the quantized rotation of a molecule. Next lecture, we're going to get into Rovibrational spectroscopy, where rotation and vibration are added together. So the molecule is doing both vibrational jumps and rotational jumps. But you can't really jump into Rovibrational without just talking about rotation itself. So today's focused in on just the rotation of the molecule, and this is the whole molecule rotating, tumbling, okay? And that motion is quantized, okay? And so this, in general, let's take a quick aside over to absorption and emission processes. There's absorption, which we've been talking about most of this time, but there's really two types of emission. So there's stimulated emission and there's spontaneous emission. And stimulated emission, well, let's just look at this and draw some waves in. So if you've got a molecule down in this lower state and a wavelength of light comes in and it matches and the symmetry matches, you might have that photon get absorbed by the molecule and jump to a higher state. So that would be absorption. And we don't use the word stimulated, but that's what it is. It's stimulated absorption. Light came in, the molecule jumps up. The light's gone, the molecule now has that energy. Then you could have stimulated emission where light, well, let's do spontaneous emission. So spontaneous emission, the molecule is in the excited state and it spits out some energy in terms of light and drops down to the lower level. So spontaneous, stimulated absorption, okay? Then we have spontaneous emission. What is stimulated emission? Stimulated emission is interesting because a photon of light comes along and hits a molecule that's in an excited state and bounces off of it, if you will. And then the molecule also emits light. So one photon comes in and two leave. Okay, so the molecule is stimulated to emit. The nice thing about it is that those photons come out in phase. So if you want to think about amplitude, the wave comes in, interacts with an excited molecule, and comes out with twice the amplitude. Or one photon, a particulate view, one photon hits the molecule that's in the excited state, and two photons come out. They have the same energy. So in the wave nature, they're in phase. In the particle nature, they have the same energy, the same direction. Okay, so that's stimulated emission. Now, look at that, though. One photon came in, two came out. Or if you think of the amplitude, one amplitude now is doubled. So that's amplification, right? And it's light. So you have light amplification by the stimulated emission of radiation. And that's what laser stands for. So LASER is light amplification by stimulated emission of radiation. So if we could take advantage of this, we could get molecules in their excited state more so than the ground state, then those photons have a higher probability of causing stimulated emission. And we'll talk about lasers more as the semester goes on. We're using lasers this week in lab. This is how this is done. In a diode laser, you use an electrical potential to create this inversion, this population inversion, and then light comes in and more photons come out. You've amplified that wavelength. So that's stimulated emission. But we also have spontaneous emission. So if we have molecules in the excited state, they spontaneously drop back down. It's not a stable situation. Nature wants to be in the lowest energy state. And if you've got an excited molecule in any manner that it's excited, it's not in its ground state, it wants to drop down. So it will happen spontaneously. And spontaneous emission is really the enemy of lasing, because for a laser, you have to have the molecules stay in the excited state long enough for photons to come in and interact with them. If they're constantly dropping down spontaneously, then you can't have a very good laser. And so the probability depends upon the transition frequency to the third power. So think about that. The probability of spontaneously jumping down depends upon how high you are, because the difference is that transition frequency. Okay. You want to know the energy equals h nu, so the energy depends upon this energy difference. The higher the energy difference cubed, if you will, is going to give you the probability of jumping down. So for electronic states, they have extremely short lifetimes. If you get a molecule in an excited state electronically, it's only going to stay there 10 to the minus 15 seconds, so a femtosecond. And it's already dropped down and spit out that photon spontaneously. So it's very difficult to have visible lasers. We can have visible lasers, but we have to work hard to get that population inversion. Vibrational states have short lifetimes, 10 to the negative 12 seconds or picoseconds. And then rotational states have really long lifetimes. And nuclear states can last for months because there's very little difference between nuclear spin states in a molecule. So we're talking about rotational energy levels. This rotational quantum number is J. So let's review. Our particle in a box quantum number was N. N was just sort of a generic quantum number too. We kind of use that for electronic states as well. But then we have the vibrational quantum numbers, which are V. And they have a subscript for whatever mode number they are. So like a CO2 has 4 vibrations, but 2 are degenerate. So it has V1, V2, and V3. So you could talk about the different vibrational states in CO2. We label those with the V quantum number and subscripts telling you what mode there are. And then the rotational motion in a molecule we call J, so the J quantum number. Now if you have a polyatomic molecule, we throw K in there as well, so J and K, but we're in this class going to only deal with diatomic rotation. So we'll just have J as our quantum number for rotation. The energy levels, here's the energy level equation. You always want to keep those handy. Okay. So the energy, as it depends upon the J quantum number, is B, which is a rotational constant, it's coming up, times J plus 1. And we leave it in that strange format of J times J plus 1, just traditionally. Okay, it's BJ squared plus BJ. Okay, but this is the way we've collected the terms, and so we leave it as J times J plus 1. So it depends upon J squared. Right? So the energy levels are not equally spaced. But notice this energy equation doesn't have mass in it or the size of the system, but all that stuff is buried inside B, the rotational constant. So this is the rotational constant here, B. And it's Planck's constant over A, pi squared, the speed of light, and I. I is the moment of inertia. So if you're going to rotate something, you have inertia, the resistance of change in momentum, right? And so you have, if you have a large molecule and you're trying to get it spinning, it has a moment of inertia. Once it's spinning, you try to slow it down, it has inertia. Okay, so it's going to be hard to slow it down, hard to spin it up if it's got a lot of mass off the axis, or if it's got a long bond length, okay, or a large size. It's hard to get something big to spin. Very easy to get something small to spin. And so this moment of inertia, the generic term here is mass times the distance from the spinning axis, r squared. So B is the rotational constant. Now in a polyatomic molecule where you have rotation around X, rotation around Y, and rotation around Z, you have 3 rotational constants, A, B, and C. But for a diatomic molecule, you just have 2 defined rotations, and 2 of those are the same. So essentially A is not defined and B equals C, so we just talk about B. So the system for a linear molecule kind of collapses down just to B being the rotational constant. But for large molecules like ethane, you have 3 different rotational constants. And so this would be something, this would be the spinning around the z-axis on ethane. Notice that these are not the bond lengths in this moment of inertia equation. So this RA here is right there. It's the distance from the spinning from the axis of rotation. You see that? And then it would be the mass of the hydrogens. So you could figure this out. This has actually got 2 different masses because this is deuterium down here. So these are deuterium and these are hydrogen up here. It's just an isotopic substitution on this molecule. And so you have RD and RA. and then you have the mass of the deuteriums and the mass of the hydrogens. And so that would be the moment of inertia for that molecule, and it would go into that equation, and that would be the rotational constant for spinning around the z-axis. I don't remember if it's A, B, or C on that one, but it's probably A. Then we have water, an asymmetric molecule. You could spin it around that CO2 axis, the C2 axis. And then we have a diatomic spinning around its center of mass. Now notice one thing that we're talking about. We're talking about pure rotation, and we want it to interact with light. And light is an oscillating electric field. Remember the last exam we had the mass, it came down to the mass of a neutron or mass of a proton. And it needed to interact with that particle. So it needed a charge to interact with. Well, since we're not doing electronic spectroscopy, or we're not vibrating and changing the dipole moment, what's going to interact with this electric field? The net dipole moment. And unless the net dipole moment rotates, then you won't have a transition. So if this is a rotation of water that we're seeing here, notice that dipole doesn't rotate. And so that rotation around the C2 axis of water will not absorb light. The other one will, rotating around X or rotating around Y, will rotate that dipole, and you will have an absorption. But if the dipole doesn't spin, then you're not going to get absorption, because you have an electric field that's oscillating, and the dipole needs to rotate with that electric field. Okay, so in this case, for a diatomic, you absolutely have a rotating dipole. So you have a hydrogen on this end, some heavy atom over there, let's say chlorine, so HCl. You've got a dipole moment, and it's rotating. And because the positive and negative charges are rotating around each other, then an electric field can interact with that. And once they're in phase, they have the right frequency, they can get an absorption. And so you can kick this molecule to a higher rotation by absorbing a photon of light. Okay. So this leads to, well, let's back up a little bit. Let's see what kind of energies this rotation has. I mean, you might imagine that they'd be pretty small. It's a molecule in space. It's not tethered to anything. You're just rotating it, right? So let's get the energy landscape. This is not in your PowerPoint. I've added this morning. So you want to probably set up a new page. And on the far left of that page, draw the two energy levels pretty far apart. And just the generic quantum numbers fine for electronic energy levels. These are going to be electronic energy levels. So this would be maybe the molecule in the highest occupied molecular orbital, electron configuration, down at that ground state. And then if we promote one electron to the LUMO, that's the first accessible excited state for that molecule. We've put one electron in the lowest unoccupied molecular orbital, and now the energy of that whole molecule is plotted as n equals 2. Okay. So this is not just the energy difference between the HOMO and LUMO orbitals. This is the energy of the whole molecule. The whole molecule in the ground electronic configuration, and then the upper state is the whole molecule's energy with one electron promoted to the LUMO. Okay. And so that would be an electronic transition that would occur in the UV or visible range of spectroscopy. So that's pretty high energy, right? You're getting close to even being able to ionize the molecule in the UV, so taking an electron completely off of it. So those electronic transitions are in the UV vis. Let's go down to that ground state and zoom in. So let's narrow our y-axis now and look at the energy levels right down there in the ground state molecule. So we're in a ground electronic state, and now we have the vibrational energy levels. So just like Google Maps, you know, you're zooming in. Now you're in a city and you can see the streets, okay? And those streets have vibrational quantum numbers. Right? And so I've drawn several levels here just to kind of get the idea. We have this scheme where we've got V1 and V2. So here's the ground state for both. This we've excited V1, but V2 is still in the ground state. Here we've excited V2. But V1 is still in the ground state. And here, since it's an equilateral of states, so this difference from here to there is V1's difference. And then one more unit of that same difference is up here. That's the second quantum in the V1. So, you know, you have all of these vibrational energy levels. If we zoomed in on that ground electronic state, we would see those vibrational energy levels. And so this is the vibrational manifold of energy levels. And those transitions are going to be in the infrared part of the spectrum. So beyond red, we're now in the infrared, the lower energy photons. Now we're going to take those molecules that are in the ground vibrational state and the ground electronic state and expand it even more. So we're going to zoom in again, scroll the mouse wheel, and now we're looking at my street with 5 houses on it. Okay, so we're really zoomed in, and those are rotational energy levels. So using the rotational quantum number, J equals 0, 1, 2, 3, 4, and they go up as J squared, so they're not equally spaced. And so those are the rotational energy levels. And those transitions occur in the microwave region of the spectrum. So even lower energy than infrared. And we're not going to do this kind of spectroscopy, pure rotation, because we don't have a microwave source. We don't have a microwave detector. We don't have a microwave spectrometer. We had one in graduate school in my research advisor's lab, and it was incredibly finicky and a pain to work. And so I had no interest in getting one up. Just me. Because we can do rotational spectroscopy on top of vibrational. Because you have rotational levels here, and you also have rotational levels here and here. And so you can have transitions that are vibration and rotation. And so that's what we'll do next time, the Rovibrational lab with carbon monoxide. Any questions about this at all? This is a really fundamental thing. You should have this image in your head. Okay? Not because I want you just to memorize stuff. This is just the landscape of spectroscopy, of everything that you do in chemistry at the molecular level. Electronic states are enormous and far apart. And vibrational levels are accessible, you know, and rotational levels are sometimes so close together you can't resolve them. And so this image in your head will explain a lot of phenomena that you see in this course, in thermodynamics even, and also in instrumental. Okay. Yes?
For rotational, so the reason why they're not equally spaced apart is because of J's being squared?
Yes, so B times J plus 1. And so that J times J plus 1, there's a J squared term. So it's J squared plus J, right? And so there's a linear piece and a squared piece. And so you just really see that as you raise the quantum number, you know, it's going, you could look at those J's and calculate the energies and see that the spacing is not linear. Yeah. Okay, so that's the energy landscape. So now we're this whole set of notes is right here on the right. We're dealing with the microwave region, pure rotation. And just to reiterate that light must be able to interact with the rotating molecule for absorption to occur. And so the molecule must possess a dipole moment. And all polar molecules possess a dipole moment. Now, we're not talking about polar bonds. Yeah, polar bonds possess dipole moments, but they could cancel each other out. So you need to be able to answer the question, is HCl polar? Is HCl polar? Yes. Is water polar? It's got 3 atoms. Is water polar? Absolutely, it's bent. But what about CO2? No, nonpolar, right? The carbon-oxygen bond is polar, but they cancel each other out because the dipoles point towards each other. Okay, so you need to be able to look at the molecule, its shape, and tell if it's polar or not. Okay. Is ethane polar? Even if it's eclipsed or staggered, it's still going to be nonpolar because all of those dipoles cancel each other out. Yeah. Okay. And so this is the key for pure rotational spectroscopy. This is really important too, because rotational levels and vibrational levels, but rotational especially, is transparent in our atmosphere because nitrogen and oxygen don't possess a permanent dipole moment. If they did, we would not be here. Why do I say that? If nitrogen and oxygen possessed a permanent dipole moment, life would not exist on Earth. More so, they would let sunlight in, but they wouldn't let the heat escape. So we would have a runaway greenhouse effect. We'd be like Venus. Okay? Because our atmosphere would hold in all of that infrared and microwave energy. Right now, our atmosphere is transparent mostly to microwave energy. It can leave. Okay? But if we had a permanent dipole moment, if for some reason our atmosphere was nitric oxide and not nitrogen and oxygen, then we would have a runaway greenhouse effect. So right now, the greenhouse gases that keep us warm at night are water mostly, and then the CO2. But water is the primary greenhouse gas that keeps our planet comfy at night. We'd freeze at night if we didn't have a greenhouse effect, because as soon as the sun goes down, all that heat would leave, and we would freeze before the sun came back up. Okay. So the selection rules. Let's talk about spectroscopy now. We have this manifold here, and our selection rules are plus or minus 1. So not 1, 3, 5, 7, 9. It's just plus or minus 1. And so let's talk about that for a little bit. Okay, and also the transition equation. This is how you would set up the transition equation. And we'll do some of these in the notes today. So we have, if it's plus or minus 1, then we can solve for the transition equation. So J plus 1 minus J. Okay, so you set up the energy equation with J plus 1 everywhere there's a J, and then you subtract the energy equation with unchanged. And the result of that is 2B times J plus 1. So this is the transition equation. You see it's in red. It matches that word. Transition equation is right there. And that tells us what the energies are and the differences between these energy levels. Okay. So since our transitions are plus 1 or minus 1, we just have arrows that go to adjacent levels. So if J is equal to 0, you see down here, if J is equal to 0, then the transition from 0 to 1, you put 0 in here for J. And so it's 0 plus 1 times 2B. So that difference is 2B. You see that? You put a 1 in the transition equation, it's 1 plus 1, that's 2, times 2B. So 4B. If you put 2 in the transition equation, that's 3 times 2 is 6B. So you see 6B. So that's the energy differences. That's the transition equation. That's how you use it. So those are all of the transitions. Notice that the difference between those different transitions, so 4 minus 2 is 2. 6 minus 4 is 2. 8 minus 6 is 2. So this is the spacing between the transitions. It's 2B spacing. This will be important. But let's ask the question why again. The selection rules. Why? Well, again, we're talking about momentum, rotational momentum, angular momentum. And if a molecule is rotating, you've got to be able to rotate it 1 unit faster, 1 chunk of angular momentum. And light has 1 unit of angular momentum. Now, we've always been talking about the plane polarized light. But light could have an X component and a Y component, and they could be 90 degrees out of phase. And so it could go from X to Y to minus X to minus Y. And it could have circular polarization as well. And so this idea of having 1 unit of angular momentum, it's kind of easier to think of circularly polarized light, to think about this. So if you've got a molecule that's spinning, and you have light coming at that molecule that's circularly polarized, it could interact with that spinning molecule. And it could give it 1 unit of angular momentum. It could give it a kick and spin it faster. And so you kind of see the arrows here. We have the spinning molecule with an arrow there and light coming in with an arrow there. And now it has 2 little arrows. You see those? So this is kind of to indicate that this little arrow plus that little arrow gives you a kick, and now you're spinning with twice the speed, if you will. Okay. And so the light can give it a kick and cause it to spin faster, and so that would be the angular momentum of light being added to the molecule. But what if light was going in the opposite direction? You could cause it to emit, right? Stimulated emission. And so it could drop that molecule, it could slow it down. So molecule's spinning this way, and light comes in spinning the other way. It hits that molecule, slows it down, 2 photons of light carry on. Okay. And so it could cancel out. And so Raman transitions involve 2 photons. So what do you think the scattering selection rules are? So you've got 2 photons of light. How many units of angular momentum are you going to have? 2 units of angular momentum. So there are 3 possibilities, right? You could have both photons of light have the same sense of spin, same units of angular momentum, so it would bump it up +2. Or they could cancel each other out and have a net of 0. And they could have also going 2 against the molecule and have a -2. So those are our selection rules for scattering. Raman would be the plus or minus 2, and 0 would be what? What's that? Rayleigh. Exactly, Rayleigh scattering. Okay, so you can have Rayleigh scattering where the angular momentum of light cancels out, or you can have Raman +2 or Raman -2. And so you could have it add to the molecule 2 units of angular momentum or take away 2 units. Now, I was unsatisfied with this whole scheme, although it makes sense. You see how we've changed direction in terms of our description of selection rules? All the way up to this point, we've used symmetry to describe our selection rules. We've had the wave function, we've looked at the symmetry, ramifications of the ground state, the excited state, the symmetry of light and how it interacts. And so I had a graduate student and I said, I want to explore this. Can we explain rotational selection rules using symmetry and not angular momentum? Now, I'm not saying angular momentum is wrong. It is a great way to explain selection rules. I saw a lot of you nodding. This makes sense. You've got something spinning, you could spin it faster if you hit it with something that has angular momentum. But just as a curiosity, I thought, would this make sense if we looked at this from a symmetry point of view? And it does. So this Victoria Spin, my graduate student a few years back, helped me write this paper where she did all of the math and so on associated with rotational wave functions and the symmetry arguments. And so we can see, you can kind of see pictorially that you have this ground state wave function, and if you were to look at it from above, you would see it's the same all the way around. This is more like a cosine for light and a cosine for the upper state. Notice how the pictures match. And that's going to give us, and if you read the paper, you'll see what those pictures represent, an allowed transition, whereas +2 is forbidden. Notice these 2 pictures don't match. And so getting into the paper and looking at what those pictures mean, you'll see that we could describe the selection rules for rotational spectroscopy using symmetry as well. And so she got her degree. Yay. Okay. So fantastic student. So let's go back to pure rotational absorption spectrum. So this would be in the microwave region. We have the levels up here. Have the energy levels here and the spectral lines down here. And so the transition frequencies are separated by 2b, twice that rotational constant, because the first difference was 2b, the next one was 4, the next one was 6. And so that's the location of these lines. If this is 0, this one's at 2b, then this one comes in at 4b, this one comes in at 6b, then 8, right? So the difference between all of those peaks is 2b. So if you were to plot that spectrum based upon wave number, which is proportional to energy, then they would be equally spaced. And so this would be a beautiful spectrum that you would get in the microwave region. When we take the infrared spectrum of carbon monoxide, you see the same beautiful spectrum. It's just, instead of starting at 0, it starts at the vibrational transition. And so this spectrum gives many, many measurements of B, which is essentially giving you many measurements of the mass or the bond length, the information of the molecule. And so we could use rotational spectroscopy to get the structure of small molecules. And I say small molecules because pretty soon you have only 3 rotations. And so there's your 3 equations. And you have no maximum to the unknowns. You have, in a large molecule like ethane, you've got 6 CH bonds and a CC bond. And you can't get all of those unknowns from just 3 rotational spectra. But you could put deuterium in there. And so now you have kind of a new molecule in terms of mass, but no different bond lengths. Now wait a second. Putting deuterium instead of hydrogen doesn't change the bond length? No. Why? Why is the bond length the same if I change from hydrogen to deuterium? What governs the bond lengths in a molecule? Yeah, the electrons and the protons, or the electrons and the nuclei. And all we've done with the nucleus of deuterium is we've just added a neutron. We haven't changed any charged particle, or we haven't changed the charge of that nucleus. And so the bond length for a carbon-deuterium bond is the same as the bond length for a carbon-hydrogen bond, because it's the Coulombic attraction that creates the bond lengths. So we could go through ethane and we could change out the hydrogens for deuteriums, do the rotational spectra for all those different isotopes. And for the carbon, we could change out from carbon-12 to carbon-13, and we could get different rotational spectra. And that's what they did in the early to mid 20th century. So the 1900s, they went through and determined the structure for all of these really small molecules. Now it's pretty easy to go into Gaussian, okay? And you can match a lot of the other kinds of spectra if you get the right geometry. And if you're matching other kinds of spectra, you've got the geometry right. And the bond lengths and angles are pretty good in Gaussian. They're within experimental error. So we're doing pretty well. Now for exotic molecules like cyclopropane and so on with strained rings and so on, Gaussian doesn't do as well. Okay, so you may still want to look at the experimental evidence for those. So we've established quite well in this course that Raman spectroscopy are really scattering itself as a 2-photon process. You have Rayleigh scattering and Raman scattering. You have the Stokes shift, where you have red-shifted light, so the molecule is at a higher energy state, and the scattered light is red-shifted, and the anti-Stokes is blue-shifted. So this is a pure rotational scattering spectrum. I think I have in the notes Raman, but I replaced that with scattering because we also have the Rayleigh line in here. So we have the levels up top and the lines down below. Always keeping that distinction in our mind between energy levels and spectral lines. Spectral lines are differences in energy levels. And so this is a nice diagram because it shows that the energy differences correspond to these different spectral lines. And so this transition here, again, it's a Raman, so it's jumping 2 levels, and that shows up right there. So light interacts with the polarizability of the molecule, which is the electron cloud, so no dipole is needed. So we could have a pure Raman or scattering spectrum of nitrogen or oxygen, but we're not going to have a pure absorption or emission spectrum in the rotational region for nitrogen and oxygen. Okay. So the scattering selection rules are 0 and plus or minus 2. These are for Raman transitions, and these are transition equations. So the Rayleigh transition equation, there is no transition. It's just elastically scattered light. So the frequency of the laser is scattered off. And so that would be this middle transition, or it's not a transition, this middle interaction. The green laser comes in, the green laser comes out. The Stokes transition, where you have the molecule going up 2 energy levels, red scattered light. So here's the transition equation right here. And then the anti-Stokes, where the green laser comes in and the molecule drops 2 levels and spits out a blue shifted photon. Here's the frequency of that blue shifted photon. It's the laser frequency plus 4b times j minus a half. And so if you want to know what the Stokes transition is starting in level 3, then you put 3 in for J and you calculate it. If you're starting at level 2, put 2 in for J and you calculate it. You can't have an anti-Stokes line starting in J equals 1. Why not? It's got to drop by 2. And so if you're starting in J equals 1, you can't drop by 2. If you're starting in 0, you can't drop by 2. So the very first anti-Stokes Raman scattered photon would have to start in J equals 2 and go down to 0. But the spacing in the Raman scattered light is 4B, and the spacing in absorption and emission is 2B. And so this is for the pure rotational scattering. Notice this full range of a rotational spectrum is less than 150 wave numbers. So you need a very good laser for this, a very narrow laser. Our laser has a full width at half maximum about 100 to 150 wave numbers. So with our laser, it's a tiny little diode laser. It doesn't have the spectral resolution to see pure rotational spectra. I mean, it was only, well, the full spectrometer was about 17,000. The laser itself may have been $6,000 or $7,000, which is dirt cheap for a spectroscopy laser. Yeah, the one of my research advisor had was a $60,000 laser. It wasn't even the full spectroscopic setup. It was just the laser itself was like $60,000. It had a 1 meter resonance tube. Okay, really high resolution, very narrow line width, and so we could do pure rotational spectroscopy, but I don't have that kind of coin. All right, so let's look at the transition equations. I know you always enjoy practice on this, so let's do the transition equation for delta J plus 1. This is where that equation came from. So we have a delta J plus 1, so we write out that energy equation. And everywhere there's a J, we put in a J plus 1. And then we subtract the energy equation without changing anything. So it's E of J plus 1 minus E of J. Pretty straightforward. Here's how you set up the problem. And from here down, it's just algebra. But if you don't know how to set it up, then you're going to screw it up. Okay. So where'd the J plus 2 come from?
J plus 1 plus 1.
Yeah, that's it. J plus 1 plus 1. So then we can multiply B through and the J's together and everything. And so we have B times that polynomial J squared plus 3J plus 2 minus BJ squared minus BJ. Let's continue to multiply through. And notice we have some nice cancellations. So the squared terms cancel. So there's no squared term in our transition equation. And we have 3 BJ over here, but we subtract 1 over here. Okay, so this right here makes this a 2. Yep. And so we end up with 2B times J plus 1. And so that's that spacing for direct absorption or emission in a pure rotational spectra of that spacing between the spectral lines is twice the rotational constant. Now, if you have a big molecule, where's size of molecule in the rotational constant? Go back in your notes. It's inside that moment of inertia. It's in the denominator. So big molecule, tiny little rotational constant. And so these peaks are too close together to resolve. And that makes sense, right? The bigger the system, the harder it is to see the quantized effects. So to see the quantized effects for rotation, we need the smallest molecules possible. We need something like carbon monoxide. Okay. And so for carbon monoxide, we have a tiny bond length, tiny masses, and so we have a big rotational constant. So our lines are spaced apart. And so they're not just spaced by B, they're spaced by 2B. So that's really nice. We can see the rotational effects, the quantized rotational effects in carbon monoxide, but we can't see them in something like iodine or some really big molecule like benzene. Okay. Let's do the Raman. So the Stokes transition equation, delta J plus 2. So we put that +2 in for the energy equation and then subtract the energy equation. So this is the setup, B times J plus 2 times J plus 3 minus B of J times J plus 1. Now the polynomial is J squared plus 5J plus 6. We get the same nice cancellation of the squared terms. These go away here and here. We lose a B from this, so it's 4. This goes to 4. And so we're going to end up with this 4B. If we pull it out, then we end up with J plus 3 halves. And again, this is just the traditional way to write it. We want the B dependence pulled out front, and we just want the J piece in parentheses. And so this is going to tell us that our Raman spectra are spaced, those spectral lines are spaced by 4B. Which is really nice. If you have a moderate rotational constant, you're having a hard time resolving it, say in a Rovibrational spectrum, something that's direct absorption or emission, then if you could get that same molecule in the gas phase and do a Raman experiment on it, those peaks are twice as far apart. They're 4B apart, and you might be able to resolve them in the Raman spectrum if you can resolve them in the direct absorption or emission infrared experiment or microwave experiment. Okay. And so let's take a Kahoot. Okay, the code is 924-5236. 924-5236. Get your thumbs warmed up. Pretty good attendance today. Anybody else? Anybody left? Okay, let's go. If a molecule lacks this, it will not have a direct absorption rotational spectrum. Red is net charge, blue is polar bonds, the orange is net dipole moment, and green is symmetric shape. So if it does not have this, if a molecule lacks this, it will not have direct absorption. Yay! Okay, net dipole moment. So it could have polar bonds and so on, but which of these molecules will have a direct absorption rotational spectrum? So now you've got to look at these molecules and see which one is corresponding to having a spectrum. Okay, a net dipole moment. So red is nitrogen, blue is CO2, orange is methane, and green is water. Very good. Now I said that the microwave region was important for the greenhouse effect, but so is the infrared. So methane and CO2 are greenhouse gases as well, but not by direct absorption of rotational lines. So they are through the vibrational spectrum. Which of these molecules will have a direct absorption rotational spectrum? Ethane, acetone, acetylene, or neon? Up the bar a little bit on this one. Remember what acetylene is? Ethine. It's the last few people. All right, it's acetone. So think about acetone. It's got that ketone in the middle. You got an oxygen on top and the methyl groups on the bottom. That's definitely polar. Now, we wouldn't be able to resolve that rotational spectrum because the molecule's too big. If we had a super high resolution laser, maybe. What are the rotational selection rules for direct absorption and emission? Rotational selection rules. 2B, 4B, delta J plus or minus 1, delta J plus or minus 2 or 0. So there's several things going on in this question, mentally. Yes, so the selection rules are the transitions that are allowed, and it's based on the quantum numbers. So what's the spacing between rotational Raman lines? Might be a slight problem with this question, but pick the one that's closest to the right answer. No. Never mind what I just said. No problem with this answer. Yeah, the spacing between the rotational Raman lines is 4B. Yeah. All right, great. So 2B is the infrared, or not the infrared, but the direct absorption, and 4B is the Raman. All right. Good deal. Somebody had a little flame going here. Yeah, very good. All right. Well, have a great day.